expert session, expert lecture session. Today we have expert Dr. Prashant Shahi sir with us. Dr. Prashant Shahi sir is presently working as assistant professor in Department of Physics in Deen Dayal Upadhyay Gorakhpur University. Before before joining Deen Dayal Upadhyay Gorakhpur University, he was working. Before joining Deen Dayal Upadhyay Gorakhpur University, he has completed his PhD from IIT BHU in 2015, and then after he completed his postdoctorate from postdoctorate of 2 years from 2016 to 2018 from Institute of Physics, Chinese Academy of Science, China, and then after he also joined Institute of Solid State Physics, University of Tokyo, Japan from February 2018, and then after he joined DDU Gorakhpur. Sir have very vast experience of research, have explored a lot of domains, and well-known expert right now in his domain. His area of research is high pressure method, energy material, superconductivity, topological insulator, magnetic material, strongly correlated systems. His contribution in the field of science and technology can be estimated by this, that he in very short span of time he has been awarded with the 4 projects sponsored by UGC and SERB with the amount of approximately 60 lakhs, and out of which he has completed one project sponsored by DST SERB which was of amount approximately 32 lakhs. His contribution in the field of research is very much significant. He has published more than 36 SCI indexed publications in reputed journals. He have contributed in many conferences and holds many administrative responsibility as well at Deen Dayal Upadhyay Technical University. Presently, he is also supervising 2 PhD students under his guidance. We are very pleased that person with such kind of the international exposure have joined us on very short notice and short invitation. I would like to thank him for from my side and from the department side that he have accepted our request to join. I request coordinator of this faculty development program, Dr. D.K. Tripathi sir, to welcome him with a bouquet. The experience which will be shared by you and the personality such kind of the with the, such kind of the exposure when join us definitely set give a kind of glimpse, a kind of motivation to us so that we can follow their footprints and achieve such kind of success. So definitely I hope that next 1.5 hours will be fruitful for you in terms of research motivation, but also as well as for personality development motivation. Thank you very much, sir.
Thank you, Mr. Prashant Pandey, for such a nice introduction, and obviously organizing committee for inviting me here. This is my first invited lecture. Actually, earlier I have got lots of invitation, but I can't able to join them. But this time I but somehow I made this time for me. Okay, so I am going to introduce you with the high pressure technique, which is actually I learned during my postdoc, and currently we are doing research and using this technique for characterizing lots of materials, like for searching some new thermoelectric materials for the superconductivity. There is a recent research paper on superconductivity that they got the room temperature TC under high pressure actually. So a high pressure technique tool is actually very important because you can uh, tune the properties of the materials by this method very easily. And but here I am going to focus on thermoelectric materials because energy as the time is passing, the consumption of energy is increasing throughout the time, and also the pollution level is also increasing because you use fossil fuels and coal. Here is the NTPC is using coal, so the pollution is also increasing. So everyone in the world is actually searching for some new materials and new way to generate energy, okay, and a clean way, green way. So so thermoelectric materials, currently it's not very, you can't able to produce lots of energy from this, but still people are working to improve the efficiency of these materials. And so we are also working on this area, and I have 4 projects, and all are actually somehow related with these materials and high pressure technique. Okay, so first I'm going to this is my university, and if you have time, recently there's a engineering department also, and there are I think 3 uh, one is like computer science, IT, and mechanical. I am not sure about it. So there are 3 systems departments are there related to engineering, and you can visit this campus. Is very big and everything is there. A very green campus, and if you have time or you get any chance, so please visit all labs and everything. You will surely going to get some uh, uh, exposure there. Okay, so this is my team. uh, uh, there are 3 assistant professors. They are from our university, and their PhD students are there who are working with us. And actually, you know, because I'm assistant professor, I have uh, uh, lots of work there, and due to that, it's very impossible for us to give all our time to research. So PhD students are very important in that kind of. Okay, so I am feeling some. I'm going to take this out, but there is a mic. Okay, sir. It's okay. So so then this is our collaborators. As Pandey sir told you that I have visited China, Japan, and my PhD was from BHU, and I have and there's some other collaborators also. Maybe later on I will discuss with you that what are the things they are doing. So but here the Professor Chang and Professor Watakus, they are working on the high pressure technique. Actually, the technique we are using here in DDU, here not here in my university, DDU University, is totally invented by Professor Yoshiba Yataku. Means there are only 2-3 labs in the world which are using that technique. He has the right everything. So so if you want to visit his lab is like, maybe later I will show you the pictures. Here you see the high pressure technique, cells and everything are there. And recently I visited from November to May for 6 months. from DDU Gorakhpur University and through DST Serve project. Okay, so let's come on the material. So I'm talking about the thermoelectric material. As I told you that as the energy, you're increasing the energy use, so the pollution is increasing, and the thermoelectric material is like you can convert heat into energy. Okay, and there are three effects, mainly basic effects are there. Due to that, we get electrical energy, or if you flow some current, you will get some temperature difference in the peatler cooling. Maybe in the CPU, you use the peatler and module and everything there. Okay, so what are these effects actually? Seebeck effect. Maybe you have all studied about it in your 12th grade. Okay, that if you put some two different materials and you create some temperature difference there, you will get some energy. Okay, voltage will be there. So that is the Seebeck effect. But Seebeck found that when he placed two materials together, two different materials, he found voltage there. So, but later on, it's found that every material have some if you create a temperature difference, you will get the voltage. Maybe very small for some materials. For some materials is big. So later on, we'll discuss is how actually which type of materials we use for thermoelectric energy and everything. Okay. So Peatler effect is just opposite of the Seebeck effect. Here, when you flow the current, you will get a cooling or heating effect. Okay, means there will be a temperature difference will be there in the material. It's just reverse of the Seebeck effect. And then the Thomson effect. Thomson effect is just if you flow current and you create temperature difference, it will maybe absorb some heat or release some heat. So that is the thing. But all the three effects are actually due to the energy difference of the carriers. Means when you heat something, you are giving energy to those materials. So some part have got higher energy, some has lower. So obviously the energy flow from higher to lower side. Okay, and that's why you get those effect. From these materials, you actually you use you generate the electricity, and or you can use it as a cooling power. So in the thermoelectric generator, what you did, you just provide some heat, waste heat, because there are lots of as you know, when the electricity flows, there's a lot of lots of heat go in the form of the heat, it wasted. So at that time, if you maybe you can use those heat to convert from these material, you can convert into energy, and you can get some power from that. Like because people are using in the small you know, like in your computer and everywhere, they are using these materials to convert the heat into energy and so on. Then the second is like thermoelectric cooler. From these material, you can when flow some current, and so you will get like hot and cold side. Okay, so the other side, if you want some you want to reduce the temperature of that box or something, fridge, there are lots of fridge which are working on this modules. Okay, and its efficiency obviously is you can calculate by QC by P, where P you are giving the power and QC the cooling capacity you are getting. Okay, so when you talk about the applications, so as I told you, mainly in space physics, because when you go outside the Earth, you will get sun, heat, and everything. So from there, you can very easily able to generate electricity and all the energy. So, and it's very good because there is no pollution is there, and then it's a very complex, and less weight, high reliability, because nothing, no part is moving, so there is no noise, nothing is there. Okay, and these are all the applications, you will find it somewhere. Then how you characterize that which material is good or which is bad thermoelectric material. So we use ZT parameter to define the either the material is good or bad. So the equation is like some S square sigma T by K E plus KL, where S is as the seebeck coefficient. As I told you, you can calculate it by temperature delta V by delta T, where delta V is just what the voltage you are getting across that material, and delta T is the temperature you are creating there. Okay. Then conductivity, electrical conductivity, everyone knows how to measure it, I think. Maybe later I will show you how you can measure it. Electrical conductivity, and then the K and KL, that part is the thermal conductivity. Okay. So this one is actually a thermal conductivity, which has two parts. One is coming from electrons, electronic thermal conductivity, and one part is actually from lattice thermal conductivity. Okay. Lattice is due to the phonons. Phonons, come from vibration of the materials. Maybe you have studied this somewhere, electronics and electronics, you have studied these. So that's why I keep it very simple. Then as you can see, the ZT, the parameter I told you, is recent actually. It is found that if you achieve ZT greater than 2, the efficiency of the any instrument which is working with this will improve. Like thermoelectric generator efficiency will be improved, and then improved by like 30% more. So in recently at room temperature, bismuth telluride is used as a good thermoelectric material, and its ZT is near about 1. So our aim is to get high ZT, this figure of merit for these materials. Okay. And how, but still there is a problem. It's not like you increase the S and increase the sigma electrical conductivity and reduce the thermal conductivity, so you will get the higher ZT. Obviously you will get it according to the equation, but you know that the seebeck effect, as I told you, is totally related to the carrier concentration. So if you increase the carrier concentration, the electrons, suppose you increase the electrons in the material, so its seebeck will be goes what? Low, because there are lots of electrons will be, but the conductivity will be become good. Okay. Then again, the electronic thermal conductivity means if you increase the electrons there, so there are too much electrons are there to carry the heat from one side to other side. So thermal conductivity will also be got increased. So they are connected to each other, and you have to find a balanced position. From here you can see from this figure, like if you are increasing the carrier concentration of the material, so you can see the S is actually decreasing as you are increasing the carrier concentration. The sigma is actually increasing, and this is also increasing, but this is decreasing. So you have to found somewhere here you will find the ZT is high. You have to somehow tune the carrier concentration and other things to get the higher ZT. Okay. And for that, whatever you do, you have to there are different methods from which you can tune these properties. Like you can increase the density of electrons, or you can increase the mobility somehow, or you can change some other parameters so that the ZT, but you have to somehow get the balance so that you get the higher ZT for that material. You have to somehow tune the properties of the material. Like what you do in your electronics, you use silicon. So in silicons you do what? you make it p type or n type. So p type and n type, p type means what? You are increasing the holes as you can, so that's the n actually, that is the n. You increasing the holes, or you increasing the, or you are increasing the electrons in the n type. It's something like that. So you can tune these properties. So in your electronics, you have studied there are 3 types of materials. In the 12, I think you have studied it. That they are metals, they are insulators, and semiconductors, which lie in between the metal and insulator. So as I told you, metals means what? There are lots of electrons or holes are there. So in that case, your electrical conductivity will be very high. Your Seebeck coefficient will be low in case of metal, and but the thermal conductivity will be high because there are lots of electrons, so they can carry heat from one side to other side. So their K will be increased too much. So that is actually not a good choice. Means where you have to, if you, because you have to choose the material, which material is good, or from where I can start. So from where you can start. So metal is not a good choice. So you will go for insulators. In insulators, there are very small number of holes or electrons will be there, and in that case, the electrical conductivity is very low because there is no electron available. Conductivity will be obviously low. Then, but the Seebeck is very high, and the thermal conductivity, because there are very small number of electrons are there which can carry heat from other side, so it's also low. But due to this one, this is also not good choice. Then the third one is like what? Semiconductors. So we know semiconductors lie in between, their properties lie in between metal and insulator. So in that case, what you will find that their electrical conductivity is moderate. You can change the density of electrons or everything from according to your choice. Then according to whatever point where you get you will get the ZT high. So and the Seebeck coefficient is high. Generally in every semiconductor materials you will find that Seebeck coefficient high, and obviously their thermal conductivity is low. So if you want to work in this area, you have to choose semiconductors, and you have to increase somehow, you have to tune their properties accordingly. Okay. So what are the factors which are affecting the ZT actually? As I earlier told you, Seebeck is actually depend upon this equation, the Seebeck value, then that is the thermal conductivity, electrical conductivity, and this one is just mobility, means how electron is moving fast and slow. So you found that S, in case of this, S is actually, this is the effective mass, effective mass, because the electrons are moves in some potential, and if you put some force, something there, so they will, it's not easy for them to move, so the effective mass will be actually increased. So so in that case, if you want to increase the S, you have to increase the effective mass. Okay, and that can be done later on. I will show you that can be done by using high pressure technique. Okay, so but in this case you can see that the conductivity is actually inversely proportional to m star. So again the same thing is there, not only density of electrons we are talking about, you have to tune both the things also, how bands, because effective mass is totally related to the bands. You have a study about the bands, that when you make a crystal, the energy levels get closer, and then there will be a splitting in the energy levels. So that the bands will be there. So you have to somehow choose these parameters, or you have to tune these parameters very wisely, by some way. There are different ways to tune these things so that you will get a higher ZT. Okay. Then, as I told you, I have talk about the feedback and other things, but thermal conductivity, as I told you, in thermal conductivity there are two parts are there: electronic thermal conductivity and lattice thermal conductivity. So electronics thermal conductivity can be changed by changing the electrons, density of electrons, but it's very difficult to tune this electrons, very difficult to tune. So it's better to reduce the lattice thermal conductivity. How you can reduce it? Because lattice thermal conductivity is due to the phonons. If you somehow put higher heavy elements over there, phonons are due to the vibration of the crystal, so there the vibration will be got affected, means heavy elements, so you will get a very vibration, you're going to become low, so your KL will be reduced. So if you want to work on thermal conductivity, means so it's better to tune the lattice thermal conductivity instead of electronic thermal conductivity. Okay. Are you getting bored? समझ में आ रहा है कुछ? Okay. Then there are lots of strategies are there uh, from which you can tune the ZT. So you have to choose the materials, as I told you, with something like phonon glass, means glass has very low thermal conductivity, and you need to choose the material which has very high electrical conductivity. There are materials available already from where, and then the phonon electric type of materials. Then nano dimensional approach, nano electronics, everyone is know that you can somehow in the nano dimensional, when you go from the bulk to nano, what you do, you confine the electron movement. You confine the electron movement means you can control their mobility, you can control their density, everything you can control, means, and it can move in like a very single channel in nano electronics. So you can tune from this way, you can very easily tune the thermal ZT values of the material. Then again, band engineering, as I told you, there are two type of bands, maybe in electronics you have studied it. Light band and flat bands are generally heavy band, means effective mass will be increased in that case. So you can tune the bands accordingly by using some technique or some doping. There will be some reconstruction of the bands. Maybe they got steepest, they got flat, something will be there, and you can tune their properties accordingly. So you, and the main theme is here is just a tuning. You have to, as I told you earlier, you have to wisely tune their properties so that you get a balance between S, sigma and K. That's the main thing here. Okay. Then single valley means, suppose you have know about, did you ever heard about electron pockets? Electron pockets are there, means so suppose if there is one electron pocket is there or one hole pocket is there, so in that case what will happen, one type of electron goes from move, but suppose you have lots of in your band there are lots of valleys, means near the Fermi surface there are lots of valleys type of there, or lots of electron pockets are there. So you get the contribution from each, and actually the resultant is the sum of all the contributions. So in this case, suppose you will get the contribution from three type of electrons, and your feedback will become high in that case. Okay. So this type of material you can choose for ZT parameters, you can increase. Then again I have told about the phonon confinement. If you go from bulk to nanostructure, so you can by confining the electron, in some dimension can easily achieve the ZT greater than 3, and people are doing this. Okay. Then our main technique, what I am going to introduce here, is the high pressure technique. It's not available everywhere actually. Very few people in India are working on this, but in our university we have developed these facilities, uh, high pressure technique facility, and from this you are very easily able to, means high pressure means what? Means you are applying some pressure on material. If you apply some pressure, so obviously what will happen? Your lattice parameters in the crystals will got reduced in some direction, maybe elongate in other direction, and due to that the bands got reconstructed, and the flat, as I told you, the band gap will also decrease. So you can very easily tune the band gap of the material by applying these pressures, and when you tune the band gap, the Fermi level also changes accordingly, and the density of state, the electron density and other density will, if you there's a motion in the your Fermi level, you will get higher density of state or lower accordingly. Whatever means, it's not necessary that when you apply high pressure everything is going to increase. It depend upon the bands or everything, whatever. Okay. So so how you apply these pressure actually on materials, that is also very important. So there are different techniques, like the first one is the diamond and wheel cell. Okay. In diamond and wheel cell there are two diamonds, is something like this, and you put the material in between the diamond. As you know, diamond is very hard, so we use that property and try to apply pressure on the material. But still, if you apply like this or by two diamonds and put the material, so the pressure is not homogeneous if you apply. So for that, to create that homogeneity, we use what? We use some liquid. As you know, if you take some liquid and you apply pressure on the liquid, the pressure transmits homogeneously in all the area. Means the pressure is nearly same for a small region. If you take a small region, you put some material in the liquid and apply the pressure is very homogeneous in every part of the material. So we use here some liquid, and we apply pressure on that liquid, and we put the material in that liquid. So first you put the material in that liquid, then put it here, and then apply the pressure. So in this way, from this apparatus actually you can move up to very high, because like 200 GPa you can achieve from diamond and wheel cell. But still the problem is you are applying the pressure from two direction, so the pressure homogeneity is not there. Okay. So it's not a very homogeneous, you can say, way to apply the pressure, because it's two dimensional. Then there's another way, like cubic and wheel cell. As I told you, the Japanese professor, he has the all the patent and everything for making these materials, and he know all the things about these materials. The company come to him and use his patent to make these high pressure cells. So he's very actually rich. Okay. So so in this method actually, this is a cubic. As you are seeing, there are 6 anvils are there, and you use this type of gasket. This is MgO and other material accordingly. You choose the hardest material, so that so this gasket has a Teflon cap is there, and a Teflon tube is there. You put the some liquid medium, like we use here Daphne and other things for creating the homogeneous pressure all over the material. So you take that cap, put some liquid, put the sample tube, and then close with the cap and put it here. You will, after that, you take the gasket here and apply the pressure from 6 direction. So the pressure here is become more homogeneous than this method. But what is the problem with this? That you can't achieve more than 14 GPa from this. Recently, they have developed a new system which can achieve 25 GPa, but the there's a chances 50% chances of failure is there. Means so many times, because if you have to measure any property, you have to make the contacts. So that is the problem. If you make the contacts, you connect the wires and you put such high pressure, sometimes what happen, the contact get removed, some bad things happen, sometimes and wheels get break. So 14 GPa till, if you want to go to Photonics, is safe and very easy to handle. But they are working, and maybe in future you will find that it can also go up to very high pressure. And its size is also very big, like this one. And the diamond envy, this cell is like this size, cylinder type. But still, the space, in this one, the space is very small. So making connections in this method, in this technique, is very difficult. But in this one, it's very easy. You have a lot of space as compared to this one, so it's very easy to handle actually. And then there's another one. If you want more space, then they use piston cylinder cell. It can go up to 3 GPa, 2 to 3 GPa. If you want to just apply pressure and you want some bigger space, lots of connections, because it has also some restrictions that you can only able to make 4 connections. But in this one, as you see, there are lots of wires, 16 to 30 wires you can able to put in that cell. So you have lots of wires there, so you can make 4-5 samples measurement all together. So generally what we do, we first put the sample in the piston cylinder cell. We try to tune the properties, and if there's not too much changes are there, then we go for the cubic anvil and other things. But in our lab here in DDU University, we are using the piston cylinder cell for applying the pressure, because for measuring the thermoelectric properties, later I will show you, you need at least 10 to 6 connections, at least 6 connections you need. And with this one, it's not possible, but still we are trying to, because it's possible to make the connections 5. Later I will show you how you can able to reduce the connections, and if we somehow make some other take the wire from other sides, maybe it's possible. We are trying. Maybe in the future we will able to measure the thermoelectric and other properties from the high pressure cell. Okay, but in our lab we are using this technique. As I told you, it's very homogeneous. So that is the advantage with these cubic anvil cell and piston cylinder cell. Okay. So so what happens when you put the samples in high pressure? So these are the very simple way to characterize them, that the conductivity is actually depend upon the band gap of the material. So when you apply pressure, the generally it's not a it's not like it's not necessary that the band gap is going to decrease all the time. It's not necessary. Sometimes you will find that okay, the band gap is increasing as you are applying the pressure. So but generally the band gap decreases and when the band gap decreases, the density of electron, the Fermi level changes, then the density of state changes, and accordingly your conductivity what changes. But it depends exponentially, it change exponentially with the band gap. And in the same way, you can find that S changes with the band gap and everything. If there is a some you know if there's some recreation of the bands, maybe you get the steepest band, so the effective mass also got changed, and accordingly you will get some change in S and everything. Okay, then obviously the uh, thermal conductivity, lattice thermal conductivity depend upon pressure and depend upon bulk modulus and these things. And again the same thing, you have to tune, means it's not necessary that you will always going to get very good results, it's not necessary. So you have to choose the material very wisely, you have to and later I will told you later what that is better to first go for some theoretical calculation. You try all the things with the theory, and then if you are getting the results from theoretical calculations, good results, then you go for experiment. That is the wise of choosing the material, because it's not possible, because there are lots of materials, lots of semiconductors are there, and if you start trying for doping for all the materials, maybe sometimes you got successful, but the failure rate will be high in that case. So it's better to go for some theoretical calculation and then you go for experiments. Okay. So this is the figure I have taken from this paper, which shows that how the ZT has got improved with respect to years. Like in 2015, you can see SNSC has ZT of near about 2.5, and there is a recent paper in 2020 and 22, which because this graph is, the paper is actually old, written in 2015, so they have taken only data till 2015. But recently there is a Nature paper, Nature material paper. They have get very high, like 3 or something in lead telluride material. Okay. But still the thing is, these are good materials, means that T is high for these materials, but it is at the higher temperature side. All the materials which are have a good ZT is we are getting it higher temperature and at different phase, because when you heat the material, the phase got changed, and they have some higher ZT. So what we are doing, we are applying the pressure, and by applying the pressure, there are so many chances that the phase got changed. In that case, if the phase got changed, or we can achieve the higher temperature phase at the room temperature, then we'll get that the same type of ZT at room temperature. So we are working to get the figure of merit higher at room temperature, okay, by applying high pressure technique. Okay. And there are different class of materials are already available. Those have, but when we talk about the room temperature, and already commercialized materials, actually bismuth telluride is there. You have whatever you use in your CPU, the thermoelectric module, that is made of the bismuth telluride related materials, and its ZT is near about 1 at room temperature. So still it's a challenge to improve it to get 2 or higher at room temperature. It's a challenge for everyone. So as I told you, it's better to first calculate the electronic properties of the material by using some theoretical software or somewhere, because Nowadays there are lots of softwares are freely available on the website. One of the very famous software is Quantum Espresso, which can be used for calculating the the density of state of the material, the band structure, and their other electronic properties like thermoelectric properties and electrical conductivity. Thermoelectric and the electrical conductivity properties, you can use bolt strap code, which is also freely available on the website and everywhere freely available. So it's you can install these softwares and work. So here because we are experimentalists, so we are doing experimental part, but we, as I told you, it's wise to first do the theoretical calculation and then after it's better to go after that for the experimental calculation measurement. So we are also started working on I have give some this project to one of my PhD student, and he started exploring how we can able to calculate the properties which we are needed for this thermoelectric behavior. So and there are lots of softwares and help is available on YouTube and everywhere. You can got the software, because the installation of the software is also very tricky thing. So but still somehow they found it in YouTube, because as I told you, Quantum Espresso is a very famous software. So lots of videos available on the website. You can go for it and install the softwares with the related libraries, and you can start working on it. Just you need one computer, and for that computer also, the computer part, computer is also, because you people are from engineering background, so you know that there's a Google Cloud console is already there, Google engine is there, so you don't need to buy a computer, because if you want to run these softwares, you need a very higher configuration for if you have very lower version, like very small cores are there and RAMs are there, so the calculation will take like 2 months, 3 months, 6 months, 8 months, don't know. Means if you increase the number of lattices and everything, you increase the you make some supercells, so the calculation time will got increased accordingly. So it's better to do it on Google Cloud, which I prefer to do. And as you know, Google Cloud, first if you make the account in the Google Cloud, they will give you like $500 or $300 free. You can use it for 3 months. So what we do, because you need a credit card, so make one account, then use the other or you can, if you want, if you get expertise in that one, so in that case, because they charge you according to the how much time you are spending on that computer. So if you got expert, then make a very good configuration, choose a very good configuration, run the program for like 1 hour or half an hour, it will cost you very less, you can afford it. So that's the thing. You can so I'm going to tell you very basics about the Quantum Espresso software, which is freely available, how you are going to install it and everything. So so it's actually, this software is a mainly a first principle calculation, DFT theory. There's a DFT theory, density functional theory is there, and density functional theory is nothing but, as you maybe you have learned about the Schrodinger equation. So we just solve the Schrodinger equation by using these softwares. That's the thing. Because solving Schrodinger equation is not easy. So what you have to do, you have to do lots of approximation. Okay, because for solving like one electron system is very easy, but when the many electron system, so many electrons are there, because suppose the electron interaction is there due to the Coulomb repulsion, electron nucleus interaction is there, then other environment there's a defect and now everything will be there. So it's very difficult to solve Schrodinger equation for those. So we do approximation. We do approximation and solve these equation by using these software. And you don't need to do anything actually. The software have already everything is in there. They have done all the things. You have to just run. You have to just study the things. What are the properties you want and what are the parameters you have to choose. You have to know those things, but you don't need to know what is going on in those softwares, not too much. But if you want to be expert or you want to write a code or you want to make some softwares like this, then you need to be go very precisely in the physics of those materials. Okay. So from these you can calculate the ground state properties of the material. um, Ground state, everyone knows, is just the lowest energy state of the material. Means generally what you the materials at the 0 Kelvin, at the lowest temperature, they are in the ground. Means there is no vibrational things, nothing is there. They are just sitting there somewhere and waiting for everything. If you give some, means you are, when you are increasing the temperature, you are giving them some energy, and at that time they start vibrating and moving here and there. That is the thing. So what actually this software do, or DFT calculation do, they calculate the ground state energy. And from other softwares like Bootstrap and other things, you can calculate the properties with temperature. You choose other things accordingly. Okay. So as you can see, so these are the resources where you can found this software and everything. You can download it from there and run it. Okay. Then you are engineering background, is I think you don't need to learn these things, how to install and everything. You can search if you have any problem. You can search on the website and YouTube and everywhere. It's very easy to install for you, at least. For us it's difficult. For those who are not from that background, it's sometimes it become easy, because as I told you, these softwares are actually written for the Linux system. There are some binaries are there for Windows and other platforms, but those are not very, you can updated. They are not updated all the time. So the Linux version, always you get the new version every year. Okay. So it's better to run on the Linux system, and I think you people work on the Linux system. No. Okay. So that's why it's complicated. So because running installing things in Windows is very easy, but when you go for the Linux system, it's very complicated. If there's some error or something, it's very difficult to find that from where that error is coming. Okay. So you can download and install accordingly. If you have any problem, you can contact me, because I have tried too much and somehow we have able to get it right. Okay. We will be able to install it. Okay. So these are the commands you use in the Linux system: sudo and update, sudo git, and all these things. And also for running these softwares, you need libraries, mathematical libraries, to solve the these mathematical problems. And recently the Intel library, MKL library, and the MPI, Intel compiler, they are the best. Recently they have people are using it, and they have very good performance as compared to the Linux. Have already, there are some other compilers like G-Photon and other things. So it's better to use Intel, and you can install it very easily Intel from the Intel website. It's free of cost. Okay. So again, as I told you, if there is a problem with the installation, So you know the Oracle VirtualBox, everyone knows. So you can download because there are lots of research communities are there which they are following these type of problems. So they do what? They make install these softwares in some system, Linux system, and then make the copy of that one, and it's available all over the website. So many websites you can download from there, and you can put it in directly in the VirtualBox, and you will get everything. Like all the softwares are already installed. You don't need to do it. Just run the program. That's the things. Okay, and there are different approaches there. So as I told you, the Linux system is the best for this one, and you can also use on the other, but the versions are old there. And as I told you, it's better to run parallel, means cores of your computer. The more the core you have, you can distribute your work in so on every core, the time will become less. So as you can see that if you increase the core, your time is going decreasing and decreasing. Means you can very easily able to calculate in very small time. But with one core, two core, you take very long time. Okay. So these are the thing. As I told you, quantum explosive is just like a box. Everything is there. You just need to put some input, and you will get output. And the output is the ground state calculation, the electronic properties, the band calculation, whatever you will do it. So I'm not going to as I told you, I'm the experimentalist, so I'm not going in deep in the theoretical calculation. So but still you can see that what input you actually give. You just don't need to give all the information. You just need to, if you know the structure of your material, you can calculate everything. Like silicon, what are the lattice parameters they have, what are the atomic positions. These two things if you know, and you can make the input file, and you can put in the quantum espresso. You give the input, and you will get some output in the form of the properties of the material or everything. Okay. So these are the common workflow. Means you give the input with this command on the instrument and get the output. I think what's the time? Okay. So I am just because we have not too much time. How much time we have left?
So we have 15 minutes.
15 minutes. Okay. So I'm skipping these slides. You can work on it if you are interested. If anyone is interested, yes, you can contact me. I will help you with everything. Okay. So these are the examples of the input files. These are different. As you can see, this is a simple input file. They have these prefixes. This one is for silicon actually. So the calculation, what calculation you want to, you will get these things very easily on the quantum access website, that what calculation. Then you need pseudo directory, pseudo potential, your lattice parameter, what type of structure it has, you can and what are the atomic positions they have, and accordingly you can calculate the properties. This is the simple input file. Then there are lots of things are there. You for calculating the self ground state properties. First, I'm going to tell you the whole thing. Actually, the whole summary of this thing. That what actually you do in this, you get the CIF file. You can download it from anywhere. There's lots of website from where you can able to download the structure file of the material. Okay, like material explorer is there, a flow is there. You can download the CIF file, and there's also there's a project on the materials project. Its name is material project, where you can put the CIF file, and it will automatically generate the input file for your theoretical calculation. You don't need to put all the parameters. You just download the CIF file and go to the another website and just give them the CIF file. They will generate the input file for you for what type of calculation you want to do. Accordingly, they will generate the input. and you can just need to run the program by a single command. Okay, so if you so what is the summary? Summary is that what you do actually, you take the CIF file, structure file. First, you do a relax and VC relax calculation. What is relax and VC relax? Relax is just you optimize the atomic positions. That is the relax. After that, you optimize the lattice parameters, and then you calculate. After that, you calculate the ground state property. That's a way of calculating the properties. So first you optimize their lattice parameter and atomic positions, and then after that you calculate their ground state properties. So this is the summary actually, and then you will get all from that ground state wave equation. You can electron density, you can able to calculate all their properties like band structure, the other density of state, the thermoelectric and the thermal conductivity and everything. Okay, so these are the optimizing, how you can optimize. You can see in this figure how they are optimized, the positions and everything. This is the band structure calculated for graphene. Okay, graphene is also very important in your electronics. I think these days lots of research work is going on the graphene. Then experimental investigation. What we are doing, the step is like we grow single crystals of the materials, and then we do what? We just measure their properties. So for growing single crystals, there are lots of way you can grow, but the easiest way is CVT method. The chemical vapor transfer. There are lots of methods are there, but what we are using, that is the CVT. So in the CVT, you do what? You take the material, and use some transport agent, mix it with that one. That transport agent do what? It vaporize your material, whatever material you want to do, and when you create a temperature difference, the material grow from the hotter side and got accumulated at the colder side, and at the colder side you will find that the crystals will grow. So this is the 2-zone furnace. We are from this. We are this is the quartz tube. We do what? We mix the material with the transport agent. The transport agent is any material which can able to make it in the gaseous form. You have to choose that transport agent accordingly, and then you do what? You create the temperature difference across this, and you will get the crystal at the colder side. And you have to means how you choose the temperature for these material, which temperature you need. So you need to go for the phase diagram, and there is a website. You can check their phase diagram at which temperature what phase exists, coexist, and you have to choose that temperature accordingly. Okay. So this is the step for the crystal growth. We weigh the material, then we put in the glove box, because these are generally metals, so when you take it out, it's very easily is got oxidized. So we do all the mixing and everything in the glove box. Glove box means there's a control environment is there. You can use either argon and other things. Okay. Then you put that you seal the sample in the vacuum, because again, if you heat anything, any metal on this atmosphere, it got oxidized, and we generally making like bismuth telluride. Bismuth is there, telluride is there, but there is no oxygen, germanium or something. So you need to create a vacuum over there, so there's no other gases will be available for react them. So there is only 2 materials are there which are going react, and you will get the crystal of those materials. Okay, and then you do XRD, and from the XRD you do the some ritual refinement of those materials, and you get what that your phase is actually okay or not. You can confirm from this refinement. So if you get the good phase, means your desired phase, then after that you start the measurement. So first, the electrical conductivity measurement. I think everyone knows how there are two methods: two probe method and four probe method. In the two probe method, generally, if you do the two probe measurement, what happen that you calculate the contact resistance also. So it's better if you want to measure electrical conductivity. It's uh, good to use four probe method. In four probe method, you actually remove those contact resistances, means you put the current from across the sample from some lead and then measure the voltage accordingly. Then how you do the feedback measurement and ambient and high pressure, what we are doing in our lab is just we make this type of stage. Okay, in this stage we put the sample and we create a temperature difference in between them by using some strain gauge heater. Okay, here you can, this is the heater. So when you heat it from this part, there will be a temperature gradient, and when there will be a temperature gradient, you measure the voltage uh, of that sample, and you also want to need what temperature difference is there, because S, as I told you, S is what, delta V by delta T. So delta V is this one and delta T is this one, means what is the temperature difference between them. From there you can very easily able to and this is a very unique technique. Unique means this is the homemade setup, and in the market if you go for any instrument, its price is like crores, 1 crore or something for this. And this setup in all lab has made for more than like 5 lakhs. Okay, so the setups which are commercially available, for that you need very big crystals, very big samples. But this one you can see I have shown the dimensions, like 5 mm stage is there, 2 mm. So sample size is like 1 mm. So you can measure 1 mm sample very easily from these setup, and this facility is actually available. Then you make some LabVIEW programming. LabVIEW, have you heard about the LabVIEW? So LabVIEW programming, and you can able to get the data from your all the instrument very easily. Okay, these are the results which we from our device which we have done for like ZRT5 and some chromium based materials with magnetic field also. So this is a single crystal we have measured because you know in the single crystal you have A, B, C, 3 directions are there. So we measured their feedback with the magnetic field direction in all the 3 directions, and we find very interesting results which we have published in physical review and other papers. Then pressure. With pressure, the same setup as I told you. We want to because the space is very small, this 5 mm in the piston cylinder cell also. So from the commercially available you know from your device, it's not possible to measure under high pressure, but from our setup it's very easy to measure it. You can this is the copper ring, there are lots of wires. I told you you can put 16 to 30 wires over there. You take this stage here and connect all the wires, all the things, and then put the cap here and then apply the pressure. Okay, so something like this. Okay, so these are the measurement we have performed under high pressure. Okay, okay, these are the pressure and these are the high pressure results are there. Then we are, as I told you, we are you know trying to integrate this setup with the for more higher pressure like 16 GP or something. Okay. Then thermal conductivity measurement. There are lots of how you do the thermal conductivity. There are different methods are there. Like generally for bulk materials they use steady state method, but steady state method have lots of problem. The problem because in if you want to measure the thermal conductivity, you need to give some heat to them, and you whatever power you are giving them, and accordingly you calculate the thermal conductivity. But what happened when you give some power or heat to some material, it start, you know, radiating the power, radiating the heat and everything. So that's why it's very difficult to measure from the steady state, means there are lots of errors will be there. So we developed in our lab a 3 omega technique from which we are measuring the thermal conductivity of the materials. And what is this setup? We create, this is the sample, we create like line heater is there. So you know, when there's a line heater, you need to give very small current or heat to them, and the radiation losses will got minimized, so the error goes very minimum. And that is the 3 omega method. Why it's called? Because when you give the current to this system, it will start heating. If you give, there's a power, then line heater, then there's a power, then you'll find the thermal fluctuation. Thermal fluctuation is there, and and you will, due to that, you will get a voltage drop, which is the third harmonic actually. 3 omega, this frequency got 3 omega, means you are giving them the omega frequency of some AC, and you are getting the voltage from the thermal conductivity part, and that is the V3 omega. Okay, so we have developed this device. We have the lock-in amplifier, and we create this type of thing. Means you do from using direct and sorry, DAC, you can remove this V omega signal, and you measure 3 omega that is actually coming from the thermal conductivity of the material. Okay, then this is the you are the electronics person, so I don't need to tell you that this is the circuit we have designed, and accordingly we put it on the, you know, easy edu software is there for designing this one, and you got the Zerber file and you upload it in GLPCB. We have made this one from, we ordered there, and we received and make the whole setup in our lab. Okay, and we have performed the measurement with 100 ohm resistance. So in 100 ohm resistance, you see there is no, only fluctuation is there. But with strain gauge is a thin film heater. Okay, so it's a thin film. So when you are putting, you are getting the 3 omega signal very easily from that setup. This is the setup we have recently made in our lab. Okay, sample requirement are there. Then again, you need to do LabVIEW programming to get the data. So we have made these programs, and you can, if you have any questions related to LabVIEW, you can contact me. I have also done lots of research in LabVIEW. Okay, so future attempt, measuring these thermal conductivity under high pressure is actually a, you know, very difficult problem, and I think if you do something like this, if you able to if you got succeed, you will going to get, you know, some, at least very, you will become very famous. Okay, and then these are the some papers we have published in some SNSC, on SNSC, like we have measured their thermal this is the actual, you know, setup, and this is the material, you know, see, these are the material. So we can able to measure the temperature difference from this one, and everything. From here we can measure the at the same time we measure the thermal Seebeck coefficient as well as the electrical conductivity. Okay, like we can put 4 wires, you can see there are 4 wires, so we are measuring the electrical conductivity by 4-wire method, and then the Seebeck also according, and these are the results with pure SNSC, and then with doping SNSC under high pressure we have measured and found that in SNSC the ZT got increased due to the, you know, and we have also measured the black phosphorus, which has isostructural with this one, and we found that okay, it's not giving the same type of result as we are getting in SNSC. It means it's not a very common that you apply pressure and you will get some good results. Okay, so this is the ZRT5. This type of crystals we have grown in our lab. There are 2 type of crystals are there. One is actually grown from CVD. Flux method is also nearly same. In flux method, what happened that you in instead of using transport some other transport as an agent, the material itself work as a transport agent. So that's called self-flux method. Okay, so we grow the two type of crystals and then perform the measurement for all with magnetic field with the same setup. And we are actually, this one is published, but these are the high pressure measurement we have performed in ZRT5 with getting some improvement in ZT, and later on these are under publication. Actually we have communicated it, and the or nearly same type of results. Okay, so sorry, you can go on the Google Scholar and ResearchGate, you will find all the things. Okay, so thank you very much. Thank you for